So part 2 is now inference of variance. We did inference of proportion, which uses z. You can use t, but you shouldn't for most cases. We just don't do it. We did inference for mean, which we use the t. You can use z for mean, but we don't. Those are, again, special cases. So in general, we're always going to use z for proportion, t for mean, and we're going to use chi squared for variance, right? For one sample. We're going to do two sample next week instead, and we'll talk about f instead there. Okay, so unlike z and t distributions, the chi-square distributions are all positive, and it's also asymmetric. So this is a picture of it down here. So your z is basically the normal curve, right? And the t is basically variations of the normal curve. Um, that vary by a degree of freedom, but they're still symmetrical basically. They're just basically spread out more or less, but they still have the same area of 1 basically. And you can get positive and negative z and t values essentially, but it's only positive when you're dealing with chi squared essentially. Okay, and it's skewed basically. We're going to use it for a few different things this semester. Okay. Degrees of freedom is n minus 1 for this one. Okay. So the confidence interval is n minus 1 times the standard deviation sample over chi squared. And you have the right and the left hand values accordingly, right? So they mean the right hand and the left hand values, the chi on the here. So you see how it says 1 minus, right? That's what it's referring to essentially. All right, so and the hypothesis tests are very similar to what we did in the past for a one sample, right? You have a left tail, a right tail, right tail, left tail, and a two tail basically. And the test statistic is this here. If you're doing a hypothesis test, compare the sample versus the population. Okay. Otherwise, you're computing chi with the computer if it's a confidence interval. Okay, so let's say we have ball bearings we purchased for our heavy equipment. So excavators, dump trucks, stuff like that, they have ball bearings. They need to be very precisely manufactured, right? So I have some ball bearings here, and I'm going to put those into my spreadsheet. So there's tab 1 from last time, here's tab 2. Okay, so we're going to need the variance, right? Otherwise s squared. What the hell just happened? These are words. General text. Text. I don't know why they did that. Variance s squared. I don't know why I did that. Okay, so equals. Alright, so variance, I'm sorry, equals var dot sample. So variance sample. Highlight all the numbers. There's our variance. Okay, the number of values is 20. Shift all these to the right. Right, so there's 20 ball bearings in my sample. Okay, so we need chi squared twice, chi squared twice. And I think that's all we need there for the confidence interval. Let's go copy the confidence interval over. So this is the formula here. Copy, paste. Okay, so we have two different chi squared values. So let's look at what we want here. So we want a 95% confidence interval. Okay, so let's go back to here. So if we want a 95% confidence interval, right? Like a one that actually kind of looks like it. And then we have 0.95. So this is 0.025. And this is 0.025, right? Okay, so we have to get to here for this chi squared. And we have to get to here for this chi squared. Okay? So to get to here, you have 0.025 and 0.095 for 0.075, right? So one of them is going to be 0.025. One of them is going to be adding those together, which is 0.0975. Okay? Okay, so we'll do the 0.975 here. I'm sorry, what am I doing? 0.097, just so I can remember which one's which. 0.25 there. Okay, so equals chi squared. So that's because there's chi and there's chi squared. So you got to be careful on that. All right, chi squared inverse, and we want right tail. Returns the inverse of the right-tailed probability. This one is the left-tailed probability. So I think if I do this one, and I put in 0.975, comma, and it wants the degrees of freedom now, I believe. So this minus 1. There we go. And if we do this one, chi squared, there we go, right-tailed, 0.025, comma, degrees of freedom minus 1. Uh-oh, what did I do wrong? I did something wrong. What did I do wrong? Oh, I didn't do inverse, did I? Oh, I didn't do an inverse. It filled in the wrong one. Because I want the actual chi squared value, right? That's the actual chi squared value. Okay. I think if I don't put the right tail, and I put the 975, it just gives me the other end. Or maybe not. No, it couldn't have been that. Yeah. Okay, anyways, there's my right and left values, essentially. Okay, so confidence interval. Let's do that over here, I guess. Put that up here. So equal parentheses. So we're going to put 19 times. I don't want to put 20 minus 1. There's my variance, right? Divided by the right value. And then equals parentheses 19 times the variance divided by the left value. There we go. So that is the confidence interval for the variance. Confidence interval for the variance. If I want the confidence interval for the standard deviation, then I just have to square root it, right? Equals the square root of that. Equals the square root of that. Okay. All right. Yeah, so if you ever have a problem reminding you which one is what, right? So our alpha here, let's write alpha here. Alpha equals 0.05, right? Because it says 95% confidence interval, it's 5% alpha, right? Because again, let's write this out here. Right? If it's 95% confidence interval, you have 5% on either end, right? Together, because that's 0.025, right? And that's 0.025. Okay. All right. So if you look, alpha divided by 2, right? Alpha divided by 2, and then 1 minus that is the other one, right? That's what those values are, essentially. Okay, so let's go back to here. And we'll write this out. So we have 0.001 109 dot 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 is less than, we'll do s squared, which is less than 0.00403 dot dot dot. And these are in millimeters, I believe, right? And then alpha was 5%. Okay. And I'm going to copy this and paste this and change this to, oh no, this is the true population. What am I doing? That's that. That was dumb of me. This is not the sample. It's the confidence interval. That's variance. Okay. I'm going to change these numbers now. So when we squared it, we got 0.03305 something. That was good enough. And then we squared it, we got 0.63348, it looks like. Keeps going. These in millimeters. Yes. Okay, so in context, the true standard, the true population standard. Okay, well actually we are 95% confident the true population standard deviation is in the confidence interval, right? Right, so basically that measure for standard deviation for the actual populations in there. 5% we might not be right. Okay, so I'll carry out a hypothesis test now. So if I do a hypothesis test, it's H sub 0, H sub A. Okay, so we're saying that the variance, so variance, what do we say in the problem here? We believe we need it to be this or less, right? We need it to be this or less to be okay, right? But you don't put the less than part into the null hypothesis. You only do the equals, right? And you want to do equals greater than here, because if it's greater than that, it's no good, right? So we're trying to prove that it is bad, basically. If it varies too much, it's not a usable product, basically, right? So we want the area equals, actually be approximate, wouldn't it? Okay, so let's make that blue and come back. Format, color, blue. Okay, where are we at? All right, so this is what we have so far. So we need a another chi-squared, right? And we need an area and an alpha, right? So this alpha is 0.025. And why is that? Well, why did it change? Well, again, this is 95%, right? But we're only looking at this tail up here, because this is the right tail case for this hypothesis test. We only want this one here, correct? Okay. So the question is, what do we want for chi-squared? Come on. Oh, I can't get the pen to stop working. That's the problem. Okay, let's go back to our notes here and get the formulas. We want the, where is it? Oh, right there. Copy, paste. There's our chi-squared that we use, right, if we are doing a hypothesis test. So we basically want the 19 times the variance, right, divided by 0.0015, I believe is what it was. Let me go back. Yes, 0015 is what we believe it is. Okay, 0015. We're good. Okay, so our area is chi squared distribution right tail, right? 0.0, I'm sorry, 975, comma, degrees of freedom minus 1. Uh-oh. Oh, why did I do that? We're supposed to use the chi-squared value. We're not. It's not the theoretical. It's the observed. This is the observed chi-squared, right? This is the theoretical up here, right? And these are the. This is the observed, basically, right? So theoretical versus observed. Okay, so the area is that there. Interesting. That is clearly way bigger than alpha, correct? So we'll go to here. So what do I have? 1988. Which equals the p-value. So clearly the p-value is greater than alpha, which is 0.025. Right? So basically, we should do not reject the null hypothesis. Our sample is not significant. We did not find enough evidence to reject the null hypothesis, right? Which means our sample is pretty ordinary. It's an expected sample. So in context, the ball bearings appear to be within spec, right? Because we didn't find enough evidence to say otherwise, because it's within the, because we didn't fail the hypothesis test, right? So does the confidence interval and significance test come to the same conclusion? Well, is 0.0015 in the confidence interval? If I look 0.00109, which, well, this is greater than that, right? So this value is in here, right? Because it's greater than this, it's less than this. So it's in the confidence interval, right? Which means it is a sample we should expect to get, right? Which means we're basically not out of spec. If we got a number that was less than or greater than, that would be a problem, because that means it's out of spec. It's not within the confidence interval we believe, basically. Okay? All right, so next week we're going to do the two sample, because it's quite a bit of material here, separately. Okay? We'll talk about F and all that, so it's not too much. And then I'll give you the exam after that. I'll give you a couple weeks to work on it when we go into the next materials, basically. Okay?